Imagine standing on solid ground, believing you understand the world beneath your feet. Mountains rise above the horizon. Oceans stretch across continents. Beneath them lies a thick shell of rock, the Earth's crust, a layer that humans have explored through drilling, mining, and geological study. For centuries, scientists believed they had a reasonably clear picture of what existed below this surface. Beneath the crust was the mantle, a vast region of hot rock slowly flowing over millions of years. And far deeper still lay the molten outer core and the solid inner core. But in the last few decades, something unexpected began to emerge from the data. Earthquakes, sudden ruptures along tectonic boundaries, send powerful waves traveling through the entire planet. These seismic waves move at different speeds depending on the material they pass through. By carefully analyzing how these waves travel, scientists can effectively see inside Earth, much like doctors use ultrasound to examine the human body. And what those waves revealed began to challenge our understanding of the planet's interior. In certain regions deep within the mantle, seismic waves were behaving strangely. As they passed through layers roughly 410 to 660 kilometers beneath the surface, they slowed dramatically. At first, geophysicists assumed this was simply a change in rock composition. But the pattern appeared again and again in seismic data collected from earthquakes all over the world. Something unusual was happening deep below Earth's crust. And the deeper scientists looked, the more intriguing the mystery became. Because hidden far beneath the continents and oceans, within a layer known as the mantle transition zone, evidence began pointing toward something astonishing. Not underground rivers, not hidden lakes, but something far larger. An enormous reservoir of water, trapped deep inside the planet itself. An ocean locked within rock. To understand how such a thing could exist, we must first explore the extraordinary conditions found inside the Earth. Our planet is structured in layers, each shaped by pressure and temperature. The outermost crust is relatively thin, averaging about 35 kilometers beneath continents and sometimes less than 10 kilometers beneath the oceans. Beneath it lies the mantle, a massive region extending nearly 2,900 kilometers toward the planet's core. Although the mantle is made of solid rock, it does not behave like the rigid stone we see at the surface. Over geological time, mantle rock flows slowly, almost like an extremely thick fluid. This slow movement drives the shifting of tectonic plates, the formation of mountains, and the eruption of volcanoes. But the mantle is not uniform. As pressure increases with depth, the minerals that make up mantle rock begin to change. Atoms rearrange themselves into new crystal structures. Minerals transform into entirely different forms of the same chemical composition. These transformations create distinct layers within the mantle. One of the most fascinating of these layers is the transition zone, located between 410 and 660 kilometers below Earth's surface. Here, pressures reach more than 20 gigapascals, over 200,000 times the atmospheric pressure at sea level. Temperatures exceed 1,500 degrees Celsius. Under such extreme conditions, common mantle minerals undergo dramatic changes. One of these minerals is olivine, a greenish crystal that makes up much of the upper mantle. As olivine is pushed deeper into the Earth by tectonic processes, the immense pressure compresses its crystal structure. At around 410 kilometers deep, it transforms into a denser mineral known as wadsleyite. Deeper still, near 520 kilometers, it transforms again, this time into a mineral called ringwoodite. For many years, ringwoodite was known only from laboratory experiments and from meteorites that had experienced intense shock pressures during cosmic collisions. Scientists believed it must exist deep within Earth's mantle. But until recently, no one had ever seen a natural sample from our planet. Then, in 2014, researchers studying a diamond discovered in Brazil made a remarkable discovery. Inside the diamond was a tiny microscopic inclusion, a trapped crystal preserved from deep within the Earth. When scientists analyzed the crystal using advanced spectroscopy techniques, they realized they were looking at something extraordinary. The crystal was natural ringwoodite. And even more astonishingly, its structure contained water. Not liquid water, but water bound within the mineral itself. This discovery provided the first direct evidence that water exists deep within Earth's mantle. And it opened the door to a far more dramatic possibility. Because ringwoodite has a unique property, it can store significant amounts of water inside its crystal lattice. Hydrogen atoms slip into tiny spaces within the mineral structure, forming hydroxyl groups bonded to oxygen atoms. To the naked eye, the mineral appears completely dry. But chemically, it can contain up to 2.5% water by weight. That may not sound like much. But when scientists considered the enormous volume of rock within the mantle transition zone, the implications became staggering. If even a small portion of this layer contains hydrated ringwoodite, the total amount of water stored there could be immense. Possibly equal to, or even greater than, all the water in Earth's surface oceans combined. But this raises an important question. How could such vast quantities of water reach such incredible depths? The answer may lie in the slow but relentless motion of Earth's tectonic plates. Our planet's surface is divided into massive plates that drift slowly across the mantle. Where these plates collide, one plate can be forced downward beneath another in a process known as subduction. When this happens, sections of oceanic crust plunge deep into the mantle. And that crust carries water with it. Ocean sediments, hydrated minerals, and water trapped within the rock itself all descend along with the sinking plate. Over millions of years, this material travels deeper and deeper into the Earth. For decades, scientists believed most of this water escaped as volcanic gases long before reaching great depths. But recent research suggests a different story. Some of that water may survive the journey. As the descending rock enters the transition zone, the intense pressure stabilizes minerals like ringwoodite that can store water efficiently. Instead of escaping, the water becomes locked into the mineral structure, stored deep within the planet. Invisible to us. Silent, but immense. Detecting this hidden reservoir is incredibly difficult. After all, no drill has ever penetrated more than about 12 kilometers into Earth's crust, barely scratching the surface compared to the hundreds of kilometers required to reach the transition zone. Instead, scientists rely on indirect clues. One of the most powerful comes from seismic waves generated by earthquakes. When these waves travel through hydrated minerals, their speed changes slightly. By analyzing these subtle differences across thousands of earthquakes, geophysicists can build detailed maps of Earth's interior. And in recent years, these maps have begun revealing something remarkable. In certain regions of the transition zone, seismic waves slow in ways that strongly suggest the presence of water-rich minerals. Not liquid oceans in underground caverns, but something equally astonishing. Rock saturated with water locked deep inside its crystal structure. A hidden ocean embedded within the mantle itself. The more scientists analyze global seismic data, the clearer this picture becomes. Our planet may contain vast reservoirs of water far below the surface, reservoirs that have remained hidden for billions of years. And if this discovery is correct, it changes something fundamental about how we understand Earth. Because the water cycle we learn about in school, the evaporation of oceans, the formation of clouds, the falling of rain, may only represent a small part of a far larger system. A planetary water cycle that extends hundreds of kilometers beneath our feet. But this revelation leads to an even deeper mystery. Because if enormous amounts of water exist inside the mantle today, then scientists must ask an even bigger question. Where did it come from in the first place? And the answer may take us back to the earliest days of our planet, when Earth itself was still forming in the chaos of the young solar system. And the answer may take us back to the earliest days of our planet, when Earth itself was still forming in the chaos of the young solar system. Around 4.5 billion years ago, the region that would eventually become Earth was filled with swirling debris. Fragments of rock, metal, and ice left over from the birth of the sun. Gravity slowly pulled this material together, forming larger and larger bodies that collided violently with one another. The early Earth was not the calm blue world we know today. It was a molten planet. Gigantic impacts released enormous amounts of energy, melting much of the surface into vast oceans of magma. Temperatures were so extreme that most volatile substances, including water, would have easily escaped into space. Yet today, Earth possesses more surface water than any other known rocky planet in the solar system. Oceans cover more than 70% of the planet's surface, shaping climate, weather systems, and the evolution of life itself. So where did all this water come from? For decades, scientists debated two main possibilities. One theory suggested that water was delivered after Earth formed, carried by icy comets and asteroids that bombarded the young planet during a period known as the Late Heavy Bombardment. These space rocks, rich in frozen water, may have gradually supplied Earth's oceans through countless impacts. Another theory proposed that water was already present in the material that formed Earth. Tiny amounts of hydrogen and oxygen trapped inside minerals may have combined during the planet's formation, eventually producing water that slowly accumulated on the surface. Both ideas were supported by evidence. But the discovery of water stored deep within mantle minerals introduced a third possibility, one that expanded the story far beyond Earth's surface. Perhaps a significant portion of Earth's water never left the interior at all. Instead, it may have been stored deep inside the planet since its earliest days. To explore this possibility, scientists began studying how water behaves under the extreme pressures found deep inside the Earth. At the surface, water is familiar and predictable. It flows as a liquid, freezes as ice, and evaporates as vapor. But under the immense pressure and heat of the mantle, water behaves very differently. Instead of existing as liquid droplets, water molecules become incorporated directly into minerals. Hydrogen atoms slip into the crystal structures of mantle minerals, bonding with oxygen atoms inside the rock. This creates what scientists call hydrous minerals, minerals that contain water as part of their chemical structure. These minerals can store remarkable amounts of water without appearing wet in any way. The rock remains completely solid. But hidden within its atomic structure, water is present. One of the most important of these minerals is ringwoodite, the same mineral discovered inside the Brazilian diamond that shocked researchers in 2014. Laboratory experiments recreating mantle conditions revealed something remarkable about ringwoodite. When exposed to high pressures and temperatures similar to those found in the transition zone, ringwoodite can absorb water extremely efficiently. Tiny spaces within its crystal lattice allow hydrogen atoms to become trapped, forming hydroxyl groups throughout the mineral. In some experiments, ringwoodite samples stored more than 1% water by weight. That might seem small, but when multiplied across the enormous volume of rock in the mantle transition zone, it becomes potentially enormous. Scientists began to realize that the transition zone could act like a massive underground sponge, absorbing and storing water transported deep into the Earth. But this discovery also helped explain another long-standing puzzle in geology. For years, seismologists studying earthquake waves noticed that certain parts of the transition zone slowed seismic waves more than expected. Solid rock transmits seismic energy efficiently, but hydrated minerals alter the way these waves travel. Water weakens the crystal structure slightly, changing how seismic energy passes through the material. The presence of water-rich ringwoodite could therefore explain these unusual seismic patterns. And when scientists began analyzing earthquake data from around the world, they found increasing evidence supporting this idea. In some regions, seismic waves slowed dramatically as they passed through the transition zone, consistent with the presence of hydrated minerals. But if water is being stored deep within the mantle, another question emerges. How does it get there? The answer lies in the powerful geological process known as subduction. Along certain tectonic boundaries, oceanic plates slide beneath neighboring plates and descend into the mantle. These sinking slabs of crust carry with them sediments, ocean floor rock, and hydrated minerals that formed when seawater interacted with the crust. As the slab descends deeper into the mantle, pressure and temperature increase. Some minerals break down, releasing water that rises back toward the surface through volcanic activity. But other minerals remain stable much deeper. These minerals can transport water hundreds of kilometers into the Earth. Eventually, much of this descending material reaches the mantle transition zone. Here, under immense pressure, minerals like ringwoodite become stable and capable of trapping water within their crystal structure. In this way, water from Earth's surface may slowly migrate deep into the planet over millions of years. But the journey does not end there. Because the deep Earth appears to operate its own version of the water cycle. When water is released from minerals inside the mantle, it can lower the melting temperature of surrounding rock. Even a small amount of water dramatically changes how rock behaves, allowing partial melting to occur. These pockets of molten rock slowly rise through the mantle. Eventually they reach the surface as magma. Volcanoes erupt, releasing gases and water vapor back into the atmosphere. Over time, that vapor condenses into clouds and rain, returning water to the oceans. And so the cycle continues. Water sinks into the mantle through subduction zones. It becomes stored within deep minerals. And eventually it returns to the surface through volcanic eruptions. But the deeper researchers looked into this process, the more surprising the implications became. Because the total amount of water potentially stored in the transition zone could be astonishing. Geophysical models suggest that if only a small fraction of the transition zone's minerals contain water, the total volume could rival, or even exceed, the amount of water in Earth's oceans. In other words, the oceans we see on the surface might represent only a portion of Earth's total water. A vast reservoir may remain hidden deep within the planet. And this hidden ocean may have existed for billions of years, quietly shaping the geological processes that define our world. But confirming this idea requires evidence from places humans can never reach. And surprisingly, some of the best clues are emerging from objects no larger than a grain of sand. Tiny fragments trapped inside diamonds, crystals that formed hundreds of kilometers beneath the Earth's surface. Because these diamonds are revealing something extraordinary about the deep interior of our planet. And what scientists discovered inside them may provide the clearest proof yet that a hidden ocean truly exists beneath Earth's crust. A discovery that could transform our understanding of how our planet works and why it is capable of sustaining life. A discovery that could transform our understanding of how our planet works and why it is capable of sustaining life. Deep beneath Earth's surface, diamonds form under immense pressure and temperature. Unlike the gemstones found in jewelry stores, many of these diamonds originate far below the crust, forming in regions of the mantle hundreds of kilometers deep. These diamonds are carried toward the surface during powerful volcanic eruptions, particularly through rare volcanic structures known as kimberlite pipes. The eruptions are incredibly fast in geological terms, allowing the diamonds to travel upward without melting or transforming. And during this rapid journey, something extraordinary happens. Tiny fragments of the deep Earth become trapped inside the growing diamond crystals. These microscopic inclusions are like sealed time capsules, preserving pieces of the mantle exactly as they existed when the diamond formed. For scientists, they provide one of the only direct glimpses into regions of the planet that lie hundreds of kilometers below our feet. When researchers began carefully analyzing these inclusions using advanced techniques such as infrared spectroscopy and high-pressure microscopy, they started finding minerals that should only exist under extreme mantle conditions. Among them were tiny grains of ringwoodite, wadsleyite, and other transition zone minerals. But what surprised scientists most was what these minerals contained. Water. Not in liquid form, but locked within the mineral structures themselves, just as laboratory experiments had predicted. These discoveries strengthened the growing evidence that large amounts of water may exist inside Earth's mantle transition zone. But the implications go far beyond simply identifying a hidden reservoir. Because water deep inside the mantle may play a crucial role in shaping the very dynamics of our planet. One of the most important geological processes on Earth is mantle convection, the slow movement of hot rock rising and cooler rock sinking within the mantle. This circulation acts like a giant engine driving plate tectonics at the surface. Water dramatically affects how this engine operates. Even small amounts of water can weaken rock, making it more flexible and easier to deform. This allows mantle material to flow more efficiently over geological time. Without water, mantle rocks would be far more rigid. And if the mantle became too rigid, the movement of tectonic plates could slow or even stop. This is not just a theoretical concern. When scientists study other rocky planets in our solar system, they notice something striking. Planets like Mars and Venus appear to lack the kind of active plate tectonics that shapes Earth's surface. Their crusts behave more like a single rigid shell rather than a collection of moving plates. Without plate tectonics, heat inside the planet cannot escape efficiently. Over time, this can lead to massive volcanic events, extreme atmospheric changes, or long-term geological stagnation. Earth, by contrast, has maintained a dynamic surface for billions of years. Continents drift. Mountains rise. Ocean floors are constantly created and recycled. Water may be one of the key ingredients that allows this system to continue operating. If large amounts of water are stored in the mantle transition zone, they could act as a stabilizing component in Earth's deep interior. A hidden reservoir quietly influencing the flow of rock and the motion of tectonic plates. But the implications extend even further. Plate tectonics also plays a major role in regulating Earth's climate. Over millions of years, tectonic processes help control the levels of carbon dioxide in the atmosphere. Carbon trapped in ocean sediments and rocks is carried into the mantle through subduction. Later, volcanic eruptions release some of this carbon back into the atmosphere. This slow carbon cycle helps stabilize global temperatures over geological timescales. Without it, Earth's climate could swing dramatically between extreme freezing and extreme heating. Water deep within the mantle may therefore contribute indirectly to the stability of Earth's climate system. In a sense, the hidden ocean beneath our feet may be helping maintain the delicate balance that allows life to exist on this planet. But this realization has also led scientists to ask a fascinating question. Is Earth unique? Or could other planets also contain hidden reservoirs of water deep inside their interiors? Recent research suggests that similar high-pressure minerals could form in the mantles of many rocky planets. If those minerals are capable of storing water in the same way as ringwoodite, then vast underground reservoirs might exist elsewhere in the universe. Some planets that appear dry at the surface may actually hide enormous quantities of water inside their interiors. And under the right conditions, that water could eventually reach the surface through volcanic eruptions or tectonic processes. This possibility has profound implications for the search for life beyond Earth. Astronomers often focus on planets located within a star's habitable zone, where temperatures allow liquid water to exist on the surface. But if water can be stored deep inside planets and gradually released over time, the range of potentially habitable worlds may be far larger than previously imagined. A planet might appear barren from space. Yet deep inside, water could be waiting, slowly cycling through the planet's interior, shaping its geology, and eventually reaching the surface. In this way, Earth's hidden ocean may not just be a geological curiosity. It may be a key piece of a much larger cosmic puzzle. Because the presence of water, whether on the surface or hidden deep underground, may determine whether a planet can remain geologically active, maintain a stable climate, and ultimately support life. And here on Earth, the deeper scientists look, the more they realize how interconnected these systems truly are. The oceans that cover our planet, the clouds that drift across the sky, the rain that falls onto continents. All of these may be linked to processes unfolding hundreds of kilometers beneath the surface. A slow, ancient cycle connecting the deep interior of the planet to the world we experience every day. And yet, despite everything scientists have learned, much about this hidden ocean remains unknown. We cannot drill deep enough to see it directly. We cannot send probes into the mantle. Instead, researchers must rely on indirect evidence, seismic waves, mineral inclusions, and laboratory experiments that recreate the extreme conditions of the deep Earth. Each discovery reveals a little more about the hidden structure of our planet. But it also reminds us how much remains unexplored. Because beneath the ground we walk on every day lies a vast and mysterious world. A world of immense pressure, scorching temperatures, and minerals unlike anything found at the surface. And within that hidden realm, there may exist one of the largest reservoirs of water on Earth. An ocean that no ship will ever sail. An ocean that no satellite will ever see. An ocean locked deep within stone, quietly shaping the planet we call home.